We're going to be talking about graphs and networks today and how we can use Wolfram Language and Wolfram Language built-in functions to explore our graphs and networks. So here's a summary of what we'll cover today. We'll start with the very basics of what a graph is, the representation of a graph in Wolfram Language and in the notebook that I'm using, the front end. How we can specify which kind of graphs we want, building graphs from data and the different file types that are supported. We'll touch on styling graphs, operations we can perform on graphs, finding community subgraphs and like connectivity of graphs. And then by the end, hopefully, we will get on to very specific kind of graph theoretic problems like the four color problem, finding particular paths, walks, and tours, like a Hamiltonian tour, for example. So I hope this will be of interest. It's a very long talk, this, and there will be some slides that I think I'll just skip through. And those of you who are watching on Big Marker can download the notebook, and you can explore that for yourselves. Those of you who are on YouTube, you can also you also have a link to download the notebook. But yes, this requires that you have Mathematica installed. You might also see some polls popping up on the screen. If you can do those, that would be great. Okay, so I'll introduce the basics and then I will kind of check in with the audience to see how I might be able to relate this more to you. Because I don't want it to be a lecture, it's a webinar. So let's get started. What is a graph in the Wolfram language? So what Wolfram language wants to do is take a graph, which is really just a collection of edges and vertices, and show that to us in a meaningful way. So that's all a graph is. Collection of objects sharing some form of relationship. The objects themselves are the nodes and the relationships between them are edges. Okay? Then we take a graph at this abstract concept, and by calling it a network, we're kind of injecting some meaning into it, where a network is a graph that has been derived from a structured process and often has meaning in particular contexts. A network can refer to a graph in which vertices and or edges have properties. So in such a case, our vertices represent real things like, I don't know, an X account or an Instagram account. And then the connections, the edges represent whether two accounts follow one another. Then you get into like whether one account follows the other account, but the other account doesn't follow the first account, that kind of thing. You have these meaningful relationships. And a graph is often the best way to represent these relationships, especially when the number of nodes gets very large. Okay, so here's some examples of where graphs and networks are used. I mean, this could go on and on, but here are just some simple examples. Well, not simple examples, but it's a small sample. So in computer science, you need to take into account relationships between nodes when you're doing database design, data mining, and web mining. I kind of already mentioned social networks. In physics, which is my background, we can model phase transitions and lattices, that kind of thing, as graphs. In ecology, you have food webs, which are really just a sort of graph. Market modeling, process chains, epidemiology, the list goes on. All right. So hopefully we can find a use case for you here, and we'll look at why Wolfram Language is such a useful tool for doing this kind of modeling, let's say. Okay, let's have a look at this. You may have heard this a lot if you're familiar with Wolfram language, if you go to a lot of these events, but the notion of symbolic objects and symbolic expressions. So an object that we call a graph object is a symbolic object, which, yes, it is composed of vertices, edges, maybe weights and styling options and stuff, but it is it is a raw atomic object. And that word atomic is important because there are these notions of atoms in the Wolfram language, and a graph is an example of an atom. Okay, so here's an example of a graph. You can see this is our graph here, some basic relationships between nodes. We can look at the input form of this and see that we have a head of graph, we have a list of vertices, and a list of edges, which are specified as to whether they are directed or undirected. Some format type here, some image size options, that kind of thing. And this is what I was talking about being atomic. Okay, you can describe them as atomic if atom q returns true. Okay, another way of saying this is that we can't extract parts of a graph. Okay, you can't go into the graph and say, okay, I want the first part of this graph, and this will return an error. Okay, for a list, for example, I can extract the first part of a list because a list is non-atomic. Therefore, if I run atom q on list, it'll be false. Okay. Now, whilst you can't extract the first, second, third part, you can extract properties, let's say. I mean, this shouldn't really say parts if we're being pedantic, because part is a meaningful Wolfram language function for which this double square bracket is just the shorthand. Okay, but what I mean by this is we're going to take these functions, vertex list, edge lists, and options, and kind of run these functions on our graph and show the information in a column. So here's the vertex list, here's the edge list, and here's the options. Okay, so we can kind of dig around and find this information, but that doesn't mean that the graph itself is non-atomic. Hopefully that makes sense. I want to show you a little bit just of how everything is communicating with one another. So if I just resize this and run it again, I have now kind of redefined this example graph. And let's look at the input form. You can see that the image size has changed. Okay, and then same here. So this information is kind of propagated through. Cool. So yeah, this graph here is just the Wolfram language kernel's best effort at visualizing what you mean when you have a list of vertices and a list of edges. Other atomic objects include like a number, a real number, an integer, a string, and a symbol. Okay. The kind of building blocks of the Wolfram language here. Okay, so let's move on. We've understood the basics of how Wolfram language interprets graphs. And now we'll look at like how we can specify this graph ourselves. And we've seen a bit of this in looking at the input form of the graph on the previous slide. So I mentioned it has a list of vertices and a list of edges, but really you only need the list of edges because if you have a list of edges, 1 goes to 2, 3 goes to 4, 4 goes to 5, etc. You've already kind of specified the vertices in that list of edges. Okay, so naming the vertices is superfluous. And then I've mentioned how edges can be directed or undirected. This is how we specify an undirected edge. You can see there's some kind of styling here to make this connection an undirected one. You can also just, instead of using the a bit long undirected edge function, you can use escape UE, escape, you get the same symbol. Same with directed edge, which, and this displays as a kind of something similar to a rule, but rules also get interpreted as directed edges. Cool. So we're going to show 3 graphs here. One uses undirected edges, one uses directed edges, and one uses rules, which are really just the same as directed edges. Uh, okay, simple enough. We can include both directed and undirected edges in our graph. Uh, what does it say here? 2 complementary directed edges are considered distinct from a corresponding undirected edge. Okay, so we'll just run this and I'll show you what this means. So in this hybrid graph, we have an undirected edge between 1 and 3, vertex 1 and vertex 3. And in this directed graph, we have 2 directed edges. Okay. Now, you might think that this undirected edge is kind of, um, it's really saying the same thing as this, but they're not considered the exact same. Okay. So if I was to check if these 2 graph objects were in fact exactly equal, it would say false. In fact, that's exactly what's next. Sometimes I get ahead of myself when I'm talking about these concepts. Any function ending in Q returns true or false. Okay. Now, as you start to program in the Wolfram language more, you might write your own code, for which you might want like a true or false test. And you can actually follow the convention yourself by adding a Q at the end of your functions. And I think this is a big step in the life of a Wolfram language programmer to write your first something Q function. And here we're just checking whether a graph is directed. And in order to be directed, every edge must be directed. And here we have an undirected edge, therefore it returns false. Okay, right, moving on. Here we just have a list of rules between objects, and then we're going to plot this in a graph with some custom edge types and vertex types, I suppose. So someone actually asked, Peter asked, can edges be labeled? We will get onto how you can do that explicitly, because the labeling here is is happening inside this iconized object. If I uniconize it, you can see the labels. Oh, it's actually used a plot theme, which kind of styles it in a certain way. I can just undo and it iconizes the object again. So yes, they can be labeled. Giorgio has asked, what if a vertex is not connected with any other, but it is part of the graph? I guess in this case, we need a list of vertices. Yeah, good point. That is actually a good point. So what I said about vertex lists being superfluous would not apply if you had an isolated vertex. Excellent point. Also got some questions from YouTube, which is great. Victor has asked, Does this seminar provide a certificate of participation? I believe it does. Um, yeah, answer the polls, answer the feedback at the end, and you should get one. Maybe someone can confirm from the marketing side, but I think so. And Abraham Campos has asked, can we use this to make flowcharts? Yeah, why not? I mean, lots of software out there you can use to make flowcharts, but I see Wolfram Language as a perfectly good tool to make flowcharts with. All it takes is really a custom vertex styling, and then you can start to use the conventional shapes for different elements of flowcharts. I think inputs have a certain shape, and questions like if statements, that kind of thing. So you'd have to do a bit of that yourself. I don't think necessarily we have any built-in like flowchart making tools, but yeah, yes, you can. And Rini has asked, how do we create a graph from a list of nodes and links, outputting only two nodes and the link between them, or three nodes and the links outgoing from them? Hmm. Create a graph from a list of nodes and links. Okay, I think I know what you want here. You kind of want the properties of one of the nodes, um, instead of the whole graph. I think you want, like, based on the graph I just made, what is this node doing, and or what are these two nodes doing? Is there a link between them? Um, so I suppose that is hinting at using functions like this, vertex list and edge list, because if I was to take vertex list here of my example graph, like I can sorry, I can find like parts 1, 2, and 3 of this, and in a sense, I think that's what you're hinting at, really. So I hope that answered your question. Because here we're saying, okay, go inside vertex list of the example graph and tell us, um, well, this is just really telling us what the first three vertices are called. And then we could, if we wanted to use that and say, okay, now I've got what they're called, we could like query the edge list with these, if that makes sense. Uh, Atul has said, do you mean a null graph? Maybe he's answering someone else's question. I'm not sure. And then Ricardo says, hi, in the example rules, where are the edge labels coming from? Where are the edge labels coming from? Great question. So let's have a look in this uniconized thing here. All right, so I'm going to make this a bit more readable. The edge labels have actually been specified in this iconized object. So sometimes I like to put each kind of label on its own line to make this a bit more readable, although you don't have to. This is a really useful property of Wolfram Language, that it does not care about indentation, but if people are looking at your code, then they probably do. So yeah, let's take an example here. Between C++ and non, we have the edge label end of line. Between slash and C, we have this edge label that's a star. So there you go, Ricardo. Okay. Thank you for the questions, everyone. Um, Faster than light memes says hi. Well, hello. Thank you for coming. Personally, don't really know what faster than light memes are, but yeah, thank you for coming, everyone. This is great. Uh, I know it's nearly approaching Christmas, but I'm glad that everyone still has the time to come to Wolfram Language webinars. It's very good to see. And I wouldn't consider myself a graph theory expert by any means, but um, in my job, if I have a use for visualizing something through a graph, I will use it. I'm always learning. I'm always learning a new function that we have um, among the six or 7,000 we have built in. So great. Moving on. This kind of answers, I believe it was Giorgio's question before, that specifying a list of vertices in addition to edges allow us to have these isolated, unconnected vertices, and we can actually, as in this case, link a vertex to itself, creating a kind of self loop. All right. And this example is well, it's quite abstract, but it just says that vertices can really be any expression, any symbolic Wolfram language expression. So here we have a graph, but one of the nodes of this graph is a graph. Another one of the nodes is a picture of the moon, and another is a string, and another is the number one. You know what I mean? So this the Wolfram language does not care. It is agnostic to what you want to put as its vertices, or edge labels, really. Robert has asked, are you going to cover how to weight edges and vertices? Yes. Yes, that is in here. Uh, Alejandro has asked, when will the Wolfram language have the ability to encode graph or get metrics for multi-layer and multiplex network? That would be very useful in comprehensive understanding of complex systems. Okay, I'm not so sure. I'm, I'm afraid I don't know the current like cutting edge of what's coming in our graph functionality, but I can try to find out. Maybe keep an eye on the release notes for the new versions, um, because there might be something in there. Barry asks, I want to visualize in 3D the relationships between two separate graph objects that are each in their own 2D plane. Hmm. Okay. I mean, we can make graphs in 3D for sure. We'll get onto that. Where the relationships between two separate graphs. I Without knowing the context of what those relationships are, I'm not entirely sure how to interpret this, but yeah, we can plot graphs in 3D, and we can connect graphs and do these kind of operations on graphs, which we will get to. Uh, I'm curious as to how do the people watching, how do you use graphs in your study or work? That would be great if you could put these things in the chat. I'm very curious to know, because I mean, yeah, I gave a talk around 2 weeks ago about real world networks. Uh, so this one isn't about real world networks. It's really about kind of getting to the core of how we provide support for different types of graphs and different types of operations that you do on graphs. But still, I think it's good to know what the audience is interested in, and how you might be able to apply Wolfram language to your work. So, as someone requested, here we have weights, which we can specify using these vertex weight and edge weight functions. So let's just run this and have a look. We've also done some styling of the vertex labels and the edge labels, where the vertex labels have been given this option vertex weight. So here we're just saying, okay, label the vertex with the weight. Makes sense. Uh, if a vertex has a weight, you want to know what that weight is, so you might as well label it on the graph, okay? And then here's just some styling. So if we were to, take this out, then we have a graph here that it does have vertex weights, because we've specified it within the graph, but there's no way to know what they are. So we should keep this label in. Okay, so that's the basics of how to specify weights. Okay, Jim F says, interested in graphs as applied to AI. Ricardo works in theoretical graph theory. Wow, especially planar graphs. Okay, awesome. Uh, Jerry Schultz says, I use graphs for function call relationships and class hierarchies in OO. I'm guessing that's object-oriented systems. And Barry, I believe he's informing me of the relationship between two graphs. So, um, okay. Wow, this is very specialized. I'm very grateful for this audience. So I'll admit some of this might be again, I don't really know how to pitch these talks sometimes because sometimes we have, new Wolfram language users, and sometimes we have experts. Now, you can still be a new Wolfram language user and an expert in something else, and maybe you're just wanting to apply Wolfram language to it. And I suppose for that type of person, what this talk should be is a way to convince you that the learning curve is not steep. Okay, I've always thought this about Wolfram language. You can learn a lot very quickly. You can get really good at it very quickly. And Sylvia has said, I'm interested in network theory and its application to economics and finance. Excellent. Right. Okay. So I remember first learning about graph theory at school. And one of the problem sheets we had one week was we had graphs printed out on a textbook page or something like that. And we actually had to, by hand, find the adjacency matrix for a graph. Okay, so adjacency matrices have a 1 if, well, a 1 at position ij if vertex vi is connected to vertex vj, and a 0 if they're not. Okay, so a bit of a boring task, I would say, to do this by hand. And what we're going to go through here is just the built-in Wolfram language functions, which really should mean that people don't do this stuff by hand, right? Especially as it scales up. Um, so we've got a very simple matrix here, and we're going to show it in matrix form. And then we're just going to find the adjacency graph corresponding to this matrix. Very simple. It's just a 3-node, 3-edge graph. And as you can see, it's symmetric. Okay, symmetric about the leading diagonal. This is just kind of converting back. So we have the graph, and now we're going to do the adjacency matrix of this adjacency graph. Okay, and then we also have to do the normal of it, and I'll explain why. Because this actually returns what's called a sparse array. Yeah, a normal of this, I'm just using the kind of postfix function application, converts it to a list of lists. Okay, As I said, symmetric matrix will produce an undirected graph. Asymmetric matrix will create a directed graph. Which kind of the directed, well, the asymmetric matrix may have certain elements that are symmetric, in which case you would have a pair of directed edges. Okay, look at this between 1 and 4. Where is this? So, yeah, here and here. This is symmetric, but because we have asymmetry elsewhere, we need a directed graph. Therefore, you need a pair of directed edges. So there's adjacency matrices. Now we'll go on to weighted adjacency matrices. Here, we don't have ones and zeros. We have weights. Okay, and whenever you have weights, you actually need to, instead of 0 representing a non-connection, you replace it with infinity. And you just need to think about that for a second. Because if you quantify a weight as like, I don't know, how hard is it to get from this edge? No, from this node to this node along this edge. If there's no edge, it's infinitely hard. Okay? That's a nice way to think about it. So here we have our weighted matrix. As you can see, we have infinities along the main diagonal. Therefore, we have no nodes that are connected to themselves. Okay, let's see if it's symmetric. Yes, it is. Again, one of those Q functions. And then let's have a weighted adjacency graph that uses this weighted matrix. Here we are. As you can see, no self loops, and we have the edge labels that are actually the weights that are in the matrix. Okay, and here we have a an asymmetric one, where we actually do have a self loop here which has weight 3. Now, what does that mean physically? Maybe someone can provide some interpretation uh, of a graph that has a self loop, but that self loop has a weight here. As you can see, like you need a weight 3 to go from 2 to 2. I'm not a graph theory expert, so maybe someone can provide a cool example of like why that makes sense in real life. So Jerry has said a symmetric adjacency matrix is actually ambiguous. It could represent a fully directed graph. Okay. Yes. I like that's a good observation. So you may lose information, in fact, by not considering like directionality if in fact you have a symmetric matrix. Barry says, yeah, the time it takes to transition that edge. Good idea. Excellent. Yeah. Thank you. Thanks, everyone. Someone said on YouTube it being harder to go around in one direction. But I mean, given that this is an edge from a node to itself, direction, I suppose, isn't a thing here. I mean, it so happens that it's been drawn from, well, clockwise from our point of view. But if this had been drawn anti-clockwise, I think it's still conveying the same information. So yeah, I believe Barry's answer of the time it takes to traverse that edge, transition that edge, makes the most sense here. I just thought of like, I don't know, the time you have to wait at a train station to get your next train. That could be a kind of edge weight. I suppose it could be a vertex weight as well. Interesting. All right. We're going to look at a different type of matrix next, called an incidence matrix. So here, admittedly, I'm less familiar with these, but we have all the information we need here. So um, a vertex is incident to an edge if it is one of the vertices to which the edge is connected. Okay. Uh, we have a row for each vertex and a column for each edge where we follow these rules. Okay. If the element of the matrix is 1, then we have an undirected edge, or I think these K's should be J's. Yeah. You can see you have 1 or -1 depending on like the which way the direction is going. And you have 2 if you have a kind of self loop. And you have -2. Okay, so here we do have a directed edge from a node to itself. So I might have just answered my own question. So as before, we've got the same kind of interoperability of the functions here. We can just take the incidence graph of our matrix and then go back again. But I want to try something here. So here we have this element here is a 2, and I want to make it a -2 and see what that does to our graph. Okay, so it has in fact directed the edge. Interesting. Okay. As you can see, I'm kind of, well, almost like a live discovery thing here. I mean, it's not groundbreaking discoveries, but it's discoveries that I often that I'll make on my own. In fact, about 5 minutes before the webinar started, I found out how to do this new thing involving typesetting, which we'll get to. Um, but yeah, I know Stephen Wolfram does these streams sometimes where he makes new um, rulological discoveries um, that may or may not be associated with Wolfram Physics project. So yeah, we have access to this wealth of information and algorithms, and we might as well use it. So we've now kind of graduated from the very basics of how to represent a graph in a matrix, how to specify a graph, and like how to label a graph, etc. Now we're kind of going to go into the like the Wolfram knowledge base kind of thing. So named graphs or types of graphs. So here we're going to start with a table of complete graphs. A complete graph means every node is connected to every other node via an edge. Okay, I often like this example because we can have this thing called graph density, which I think is probably self-explanatory what it's doing. If I were to map it over this list, uh, because of the labels here, let's see if it works. Yes, it does. Nice. So the graph density of all of these complete graphs is 1 because every node is connected to every other node. Okay, you can see how that's like a measure of density. We also have named graphs. So this is an example of a Peterson graph. Okay, so this is a built-in function with its own documentation. Those of you who are, graph theory experts, you'll probably be well aware of this. Specialist rules of how to make this graph. And yeah, I'm sure there's lots of functions like this. But then we also have graph data. So graph data kind of calls on theoretical graphs, but that don't necessarily have their own function. Okay. Um, I'd kind of like to see which other kind of graphs we have. So I'm going to do this, which this is getting all functions that end in graph. So here's our Peterson graph. Um, yeah, you can see, you can kind of pick out the ones that are named after people, let's say. Some of these we've seen already. And what's cool is it actually notices that it notes the context. So these are built-in functions. These are what are called global symbols because I've actually defined them in this notebook session. Okay. Wheel graph. That's a new one for me. So let's have a look at this. A wheel graph of order n is a graph formed by connecting a single vertex to all the vertices of a cycle of order n minus 1. Okay. In these webinars, I do tend to, a lot of the time, pull up the documentation. And I think that's important. It's important to know how to go from code to documentation to, what mistake did I make here? Let's check the documentation um, and fix it. I really like our documentation. Maybe I'm biased. If anyone has any issues, I'm open to hear them, and maybe I can make some suggestions. But with the new LLM integration we have, I think the whole notion of checking documentation is going to be a thing of the past. Now, maybe that's a bit of an optimistic claim, but given that our notebook assistant that's just come out has been trained on all of the documentation and all of the functions in the function repository and and lots more, you kind of get a automated documentation searcher as well as a coding assistant. So it's really quite revolutionary. But yeah, I appreciate not everyone will have access to the notebook assistant, but I'd recommend it. Nathan has asked, is there a function that could produce a graph out of another one by taking its dual? So thank you, Nathan, for your question. Dual, I'm guessing you mean this. So I didn't know this was a function, but I just typed in the word dual and turns out there is. So I suppose that, yes, I hope this answers your question. I think we can just perform this function on a graph and then we return the dual of the planar graph G. Okay. Can the Peterson function be applied recursively so that one can have a three-layer version of the Peterson graph? Hmm, good question. I mean, applied recursively, do you mean like Peterson graph of n and k? Because I'm hesitant to try that because this is the only documented arguments you can give it. So I'm not sure. There may be other ways you can do what you're saying there, Barry, but I'm not entirely sure. Uh, I'll just finish this last point and then I'll answer Sylvia's question. So as well as graph data on named graphs like the Pappus graph, we have example data. So here we're taking data from the Wolfram data repository, some of which is related to graphs and networks. And this one happens to be books about US politics. Okay, this is what it looks like. That's not entirely helpful because we don't know exactly what it means. So I'm going to take this and query it saying the properties. I think that's what we need. Yep, here are the properties. And then maybe I want the long description. Here it is. Edges between books represent frequent co-purchasing of books by the same buyers. Vertex property classification indicate whether they are liberal, neutral, or conservative. Okay. And that previous webinar, Real World Networks, it really went in on examples like this, maybe less political examples than this, but um, yeah, it went in on those real world networks and then did use some information and insights from them. Okay, and Sylvia asks, how is the AI assistant a Wolfram different from Wolfram Link in ChatGPT? Okay, so I believe you mean like on ChatGPT, you can pick the Wolfram. I'm not sure what to call it, like the Wolfram specific LLM, I suppose. Um, with our new notebook assistant, especially, that's been trained very comprehensively on our entire Wolfram ecosystem, let's say, and uses things like RAG, retrieval augmented generation. And yes, I think it would just be a much higher performing LLM than what you'd get outside of Wolfram. It's an LLM with Wolfram superpowers, so to speak. Okay, let's move on. So another way to kind of get graphs is taking a random graph from a distribution of graphs. Here we can find a random graph from uniform graph distribution with n vertices and m edges, so 10 vertices and 20 edges. And a Bernoulli graph distribution is another kind of graph distribution, which I'm not going to go into here, but this is the kind of thing you get. Run it again, you'll get a different one because it's random. Okay, and then here's some other examples of graph distributions. And then this is something I talked about at the start. We can just import a .gw file and show it. So yeah, and this is just one of many file formats, data formats that we support that will give you a graph. Okay, this is quite a cool example. Using this function morphological graph. So here we're getting very high level in terms of our functions and our kind of declarative statements saying, I want the morphological graph of. So there'll be lots going on under the hood here. But what we do is we take an image and kind of prep it by using these functions, pruning, thinning, binarizing, color negating, and deleting the small components of this image. And this is what we get. And then we essentially use morphological graph of this result. Like really, this is the only thing we've done here, but we have added some little styling things where we want this picture of a traffic light at each vertex. Okay, and there are a lot of edges, so this is what we get. But this has happened in seconds, right? We've gone from a kind of map image of Champaign, Illinois, where the US Wolfram HQ is, and yeah, this is what we've got out of it, where we just use this binarized as like a stepping stone to the final result. Okay, I'm going to skip this stuff on appearance because I think I've already covered it. really you're just learning about how to do style wrappers around things to get custom styling. I think it's quite self-explanatory, and I think we have more interesting stuff, and I don't want to waste our time. So, um, yeah, you can look at this yourself if you have the notebook. Lots of different color themes, etc. And then we've already seen how to label edges and vertices. This is just if you want custom labels, you use this labeled function. This is quite cool. It's you can actually control the positions of vertices using vertex coordinates. So here we've used map because we want to plot two graphs. One of them has automatic vertex coordinates, and one of them has coordinates at these 3 points. And this is what it looks like. Okay, so this is what the, you know, left to its own devices, this is what the kernel will produce. But this is kind of a forced, the vertices must be here display. And then kind of following on from this, we have this notion of embedding. So embeddings are used as options of graph layout where you can have the same graph but displayed in many different ways. So I'm going to flick through a bunch of these. You can see these are completely different looking, but they actually are encoding the same information. So here is a planar embedding, spring embedding, which incidentally looks a lot like the grid embedding. So, I mean, you could linear embedding. This is one that I can kind of infer the meaning of. It's put all the edges on one line. Okay, but the others I'm not sure what's going on. Certain embeddings have useful intrinsic properties. Spring electrical embedding attempts to match the lengths of edges to their corresponding edge weights. Oh, cool. And then this is kind of for common layouts. We actually have, instead of options, which these are, we have actual functions like layered graph plot and tree plot. Again, this is more styling information, but I will mention this. So we've seen the Peterson graph by now. So here's the Peterson graph with some custom styling. You know, we have these white disks with the edge, no, with the vertex weight inside, I think, or just the vertex number. Yeah. And then if you wanted to do operations on this graph, like find a spanning tree, it inherits those options. And then if you want to style the edges red, it's also inherited the options, but you can actually change the styling. So this is one of those kind of subtle things, but it's really useful. And then someone mentioned the 3D graphs. It's a nice interactive way to look at these things. You just use graph 3D. You can also give it kind of a list of lists here. And then there's some advice in the notebook actually of how to speed up the process of generating these. Okay. Ah, yes, because these have slightly different. This is a much larger graph, So it makes sense to make the vertices points and the edges lines instead of this. Ricardo says, is there an easy code for toggling the layout as in these examples? Do you mean like, is it easy to change the layout? Yes. Let's, because I did touch on it. Let's go back. So let's go under the hood here and see what's going on. So these embeddings are just what we say the graph layout should be. So let's take this one. Let's take this piece of code. Let's kind of take out the bits we need, and then, I don't know, let's pick one of these. Linear embedding. That's all we're doing there. We're just mapping it over many different embeddings. So yeah, thanks for your question. This is kind of the magic behind these nice visualizations. But that's really what's going on. Okay, so we've seen 3D graphs. We can also add and delete vertices and edges. Built-in function, edge delete, edge add, etc. Very basic, but let's just say we want to delete the edge between 1 and 2. Nah, it's gone. And then this is one I'm not as familiar with, but we have vertex contract. So I think I can tell what's going to happen here, but we want to contract the vertices 1 and 4, and we just end up with this. An edge contracting 2 and 3. Okay, so now the third vertex kind of is no longer existing because we have contracted the edge that connected 2 to 3. Okay, and these are the operations that I wanted to talk about before. You know, we've seen how you can find the dual planar graph of something. It's a lot of functions like this, right? Simple graph. A graph is only simple if it has no self loops, so this would remove the self loops. Reverse graph reverses the direction of all undirected edges. Okay. Directed graph converts all edges to directed edges, and this does the opposite. Line graph creates a new graph where the edges of the original graph are swapped for vertices and vertex adjacencies are swapped for edges. Interesting. This is a kind of a tricky one to imagine, I think. I do have the documentation ready because I was trying to picture it in my mind earlier. So let's have a look at this example. So here's our graph. So these two vertices in the new graph, the line graph, are adjacent because their edges are sharing a common vertex. Hopefully you can see that. This is one of those examples I've seen where it's like a good test of the LLM, the notebook assistant. Does it know how to swap the edges and vertices of graph? Because you can do that. You can take, edge list, vertex list, and then, I don't know, just swap them around and like insert them back into the graph and show it. Or you could just know the function line graph and that does it all for you. Okay, and let's show some of these. So we have a graph G. And here is the simple graph of G, the reverse graph of G, directed graph. You can see it's replaced this loop with two self loops that are directed. Uh, this is removed all direction. Here we have the complement, and then the graph power. So line graph isn't actually in here. And maybe someone can tell me actually why. Like, can you always do line graph of a graph, or does it have to satisfy certain conditions? I'm not actually sure. The way I was checking this myself is I actually found out this new typesetting thing because we see this graph G here, and the G is kind of written in what's called I think it's double struck. Yeah, double struck G. Oh dear, capital G. I picked the wrong one, but here we go. So here is our graph. And here is how to get this nice typesetting. If you're a mathematician, you work with, the reals, the real numbers, the complex numbers, and you want to write it. You want to define your variables and symbols accordingly. This might be something of interest to you. But yeah, if I do line graph of this, I actually get an error. So I'm open to people to tell me why this is perhaps. And this is a similar thing. So here we start off with two graphs, G1 and G2. And then we have things like graph intersection, difference, union, and disjoint union, just treating these graphs as if they are sets, right? So what's going on here? It seems the only thing in common with these two graphs is the edge between 3 and 4. Ricardo says, yes, you can always compute the line graph of a simple graph, and there is a theorem that characterizes which graphs are obtainable as line graphs of some graphs. Awesome, thank you. So let me try something. So we can take the line graph provided it's simple. Hmm. Try something else. Nice. Okay. So simple and undirected, it seems, is the requirement. Um, Thank you so much. Always learning, you see. Okay, let's look at this graph union. So this is doing what you expect. Um, Graph G1 here has no vertex 2, but the union does. Okay, like these connections here are kind of here on the graph union. Graph difference, graph disjoint union, and Boolean graph can be used more generally to apply any Boolean operator to two or more graphs. So I want to see exactly how this is applied because, okay, so you actually use Boolean graph as the wrapper and then the kind of Boolean operation as the first argument, and then your graphs as subsequent arguments. Interesting. Just going to look at okay. Gives the Boolean graph defined by the Boolean function b func on the graphs g1 to n. Okay, so there's no limit here. You can do g1 all the way through to gn. Here we just happen to have two. Okay, so those of you who know your Boolean operators, you might like this one. Okay, we're about 22 minutes left, so pretty happy with how far through this we are. I think I think I've covered this stuff by now. You know, we know the different types of graphs. We can extract the well, if we can extract the vertex list and the edge list, it's not beyond the pale to think that we can do a vertex count and an edge count, right? Um, so we've seen all of this so far, and then here's just some more Q functions which return true or false depending on the type of graph it is. So this graph is complete and simple. And then we've seen directed graph Q, undirected graph Q, loop-free graph Q. Uh, and this is using a similar thing I used before for graph, but for graph Q, as it prefers me to type this out. So here are all of the different GraphQ functions that will all return true or false. And there are so many more than this in the function repository, which I encourage everyone to check out. Um, I see new ones contributed every week, honestly. And if anyone is watching who contributes these, then thank you. I think it's great. It's a great way to, I don't know, bring a bit of a, well, allow everyone to contribute to the Wolfram language. So where am I going here? Graphs and networks. Here's the function repository categorized as the graphs and networks. And then I can sort by date. So these are the, like this one was contributed last week, for example. Um, here's a periodic graph Q, just what I was saying, last 3 weeks ago by Alejandra. Okay, and you can use all of these, right? You can sometimes it's hard to know what there is a function for and what there isn't. So well, this is where the notebook assistant comes in because it's been trained on the function repository and it knows all of these. Uh, but if you don't have that, then you can go on here, search, look at categories, you know, control F. I don't know. But yeah, there's over 3,000 of these. And this is just showing us the properties that we can query on a this particular graph data. Wow. Okay. Very simple graph, but technically we could go through these over 730 different properties and find those for this graph. Okay. So this is extensive stuff. Harry Butler says, Wolfram Engine saves me decades of programming. I use Python, but the versatility of Wolfram Engine far outclasses it. Well, I happen to agree. Thank you very much for saying that. Yeah. I'm intrigued to know what kind of stuff you do using the Wolfram Engine. Um, yeah, Monica on YouTube says, didn't know there were so many kinds of graphs. Well, me neither. uh, all right. Here's a fun one. Testing whether two graphs are isomorphic. And it's kind of funny because I think everyone has some familiarity with this. Like I remember back in my childhood where everyone was trying to do this challenge where you would draw a shape or a sequence of lines without taking your pen off the paper. And whilst that's not exactly the same thing going on here, that really is like a well-known graph theoretic concept, and I'm sure people in the audience today will be able to explain that better than I could. But yeah, whether two graphs are isomorphic is really just, does a renaming of vertices make them the same thing? So these two graphs are isomorphic because just because these two um, edges are crossed over, they could just as easily be not crossed over and we'd have the exact same graph. Okay, that's what isomorphic means. And then not only can we just check for isomorphism, we can find the isomorphism between two graphs, and this gives us a vertex renaming. Okay, so here we've just, as you can see, it's exactly the same up until vertex 7 and 8, where we just need to swap them around. Okay. In a similar way, if you um, you might want to find the connectedness of a network where vertices vi and vj are in the same component if there is a path from vi to vj. Okay, so here we get a list. Yeah, this graph here, you can see that, let's say this is 1, 3, 5. There are no connections between this and 2, 4, and 6. They each make up separate connected components. And then this works slightly differently for directed graphs because we're kind of um, by making the graph directed, we're kind of not allowing certain components to be connected because there is no directed path from to another. And then this is using this really useful function, highlight graph, which I used a lot in my real world networks talk. Um, because not only, like, it's so useful because you can tell it what to highlight. It's not like it's not as if it highlights um, the same thing every time. So here we just give it the graph. Let me see here. So if we look at the documentation, I think what we're doing here is an example of uh, the second use case here, where we have the graph G, which is our weighted adjacency graph, but then we highlight using the symbolic wrappers uh, WJ, which are the connected components. Okay, so here it's going to highlight the connected components. Okay, so here it's all connected, but we can look on the documentation for some kind of cooler examples of highlight graph. Uh, and you can look at the recording of the not advancing, real world networks, analyzing real world networks on YouTube if you want to see more of this. Yeah. So here it's we've specified that it should highlight the subgraphs. of G that correspond to different communities uh, that are defined by these. Okay, it's a really useful bit of functionality there. And it kind of links into Wolfram's whole ethos of, yes, we're the largest collection of algorithms in the world. And we're actually at a point now where it's so declarative, where it kind of automates that process of algorithm choosing. Um, provided you know what to give to the function. But yes, uh, yeah, sometimes you need to know what to give to the function. Sometimes it just automates that. Um, oh, Georgios has asked, is there a way to produce random graphs that follow a certain distribution, e.g. Erdos-Rényi graphs? Yes, there is. So maybe I skipped by this a bit too quickly, but it's here somewhere. um, Here we go. So yes, this is an example of a graph distribution which keeps edges when you like flip a coin with probability p. I believe it's these that are called. It's another word for Erdos-Rényi graphs, but I might be wrong. But yeah, this is what you want, Jojo. Phil says on YouTube, I had an art class as a child where we drew isomorphic letters in 3D. Wow. Okay. Um, y- yeah, so I think I was just about here, um, where this is playing on the idea of edge weights and then finding distances from those. But I think I'll move on to make sure we can get through to the end. This is a way we can force graphs to be displayed if in fact they are very large and they just kind of appear in this summary box. So we have to use graph plot on this to force it to display fully. There we go. And this is quite a cool example of where we only label um, certain vertices based on some criteria. Okay, so this is from the example data repository of Euclid's Elements, and I believe we're only labeling the graph provided it has degree. Um, oh, it has a degree of at least some value, right? So here, when this is 1, they're all labeled, but then I can slide this, and then fewer and fewer of them are labeled. And then well, if we slid this up to the maximum, we would end up with only one um, labeled vertex. So you can think of this as the axiom from which the most other axioms follow. Okay, I believe this word rules function has been defined elsewhere, but this is an example, quick one, of how we can use community graph plot to find like clusters within a graph. Um, so I believe this is finding synonyms of words. Looks like a very large graph. I'm just going to see what. Okay. So this is the graph. Communities are quite easy to identify in this, and like community graph plot just makes them a lot more obvious. As you can see, I'm having to go kind of deeper and deeper inside this nested function to see what's going on here. Okay. Okay. So it's really just finding similar words, and the similarity is represented by an edge in the graph. Again, highlight graph, we can highlight the communities in different colors. I think I'll skip this because I did talk about this a lot in my other talk. Um, we'll get on to the problem solving. So yeah, I really don't have that much time left. So we can we'll focus on this one. So a planar graph is a graph that can be drawn in the plane with no intersecting edges. All right. According to the four color theorem, I believe this is a link to the Wikipedia. At most, four colors are required to color any loopless planar graph such that no two adjacent faces share the same color. Okay. Uh, Here's an example of the United States as a four color map, which is quite cool. And then we're going to actually demonstrate this, like demonstrate that this is in fact true. I don't think we're going to prove it's true here for all graphs because that's well, maybe it hasn't been proved. It is a theorem after all. Um, okay, maybe it has been verified. I'm just glancing at the Wikipedia right now. Basically, I'm not as familiar with this one, but we'll be demonstrating that it's true for a certain case here. So we define a mesh using this function Delaunay mesh, and then we want to make the mesh connectivity graph of this mesh. Okay, this is using random reals, so we can run it again if we want a slightly different one. Okay, this faces and colors symbol, we're going to define the outer vertices and ultimately make a association of faces to their colors. Okay, we're using this association thread of the planar face list, i.e. the faces, and then the colors which are used by find planar coloring. Okay. When we're making sure that we select vertices that are the outer vertices. Okay, cool. So as you can see, these three vertices represent a face. Okay, 0, 1, 0, 3, 0, 6. You can think of that as a kind of triangle. Maybe it's this one. Um, so that's a face, and that will be colored in this color. All right. And this is just a note here. The planar face list includes the outside face, the region outside the outermost vertices. Okay, and then we want to plot the results. So lots of this code is just styling, and really the meat of this is going on in the polygon. Um, like polygon is being applied to the keys of faces and colors. But yeah, the main thing I want you to understand is what's going on here. And a lot of the hard work is being done by these new functions, planar faceless and planar coloring. So let's plot the result. There we go. Where it's nicely been labeled with 3 colors. So it actually only needed 3 colors for this. So we could go back, make a new graph. Well, let's do it. Completely new graph. We'll define a new faces and colors, and we'll run this again. Okay, so it still only needed 3 colors. So yeah, I mean, if you have the notebook, you can have fun with this and see how complicated a graph you can generate. I haven't really used these functions before, Delaunay mesh. But yeah, if you're more familiar with this, or even if you're not, you can play around with these parameters and see what you can generate here. Okay, any questions on this? Ricardo has said it's been proved with computer assistance checking several thousands of cases. No pen and paper proof are currently known. Okay. So is that to say that like there were cases that were believed to not um, satisfy this, and then the computer found that they did? That's my understanding of what you said. The Apple-Haken proof proceeds by analyzing a very large number of reducible configurations. This was improved upon in 1997. Uh, okay. Okay, mathematicians boiled it down to checking thousands of cases, then had a computer check them all. Great. Thank you, Ricardo. This is really helpful. But yeah, that's the only problem we'll have time to solve today. If you have the notebook, you can look at some more of them. Vertex coloring, edge coloring, finding walks, paths, and tours, cycles, traveling salesman problem. This is a classic. I talked about this flow networks last time. But yeah, I did think I wouldn't get through all of the examples today. But I hope you found a use case within all this. And I've got a summary on screen here.